A constant, limitless supply of energy is available from the sun in the form of solar energy. As global energy demand rises, how can we collect this energy in space and beam it efficiently to Earth in a cost-effective and environmentally friendly manner? The answer? Space-based solar power. At the Georgia Institute of Technology, an innovative solution to the space-based solar power problem has been developed by School of Aerospace Engineering professor Dr. Komarath and the Experimental Aerodynamics and Concepts Group under his direction. The space power grid is an evolutionary approach to space-based solar power that synergizes terrestrial renewable energy sources with space solar power. The space power grid features initially no space-based power generation. A constellation of low to mid-Earth orbit satellites would help terrestrial renewable energy plants, such as solar and wind plants, by allowing these plants to trade energy and smooth cyclic fluctuations in power. Through the space power grid network, terrestrial renewable energy sources can eliminate the need for these plants to have fossil fuel-based auxiliary generators, creating a greener alternative to helping meet global energy demands. By beaming to locations such as remote islands, where demand for energy is high, the space power grid can provide early revenue generation. The Georgia Tech approach proposes beaming using millimeter waves around a frequency of 220 GHz. Millimeter wave beaming would decrease antenna and receiver sizes, greatly reducing the mass of the spacecraft and in turn, overall system costs. The focus on an evolutionary development that grows as market demand dictates seeks to eliminate the large cost of first power barrier facing many proposed architectures. The first phase of the space power grid architecture features no space-based power generation. Rather, this stage focuses on the efficient transfer of energy among terrestrial energy plants. A constellation of initially around 20 low to mid-Earth orbit satellites would eventually grow to around 100 satellites and include roughly 100 ground facilities over 17 years. The second phase, beginning 17 years after project start, introduces space-based power generation. By utilizing the infrastructure already established by the first phase, the Phase 2 satellites can replace the Phase 1 satellites as market demand allows. The final phase, starting sometime after the first 17 years as technology allows, would introduce large, high-altitude, ultralight solar collectors. These collectors would reflect unconverted solar energy to the low Earth orbit constellation for beaming to ground. The advantage being that large amounts of energy can be collected with only a few large collectors, with minimal losses in reflecting to the SPG constellation, as there is nothing in space to absorb the solar energy. The solar energy would then be converted to millimeter wave before being relayed to ground, allowing the system to eventually reach terawatt global power production. In order to illustrate the efficient transfer of energy using millimeter waves, the Georgia Tech Space Power Grid team proposes a US-Indo demonstration of space-to-space wireless power beaming. Using SDK satellite tracking software, a model of this demonstration has been developed. Using 4 satellites and 4 ground locations in the United States, India, and 2 other locations, continuous beaming capability has been illustrated using near-equatorial satellites at a mid-Earth orbit altitude, showing that the SPG concept would only require a modest initial investment. The space power grid is an innovative evolutionary approach to space solar power, utilizing large-scale international cooperation to efficiently deliver power across the globe. With various technological improvements, it could offer an environmentally friendly and economically viable solution to helping meet rising global energy demands in the future.